Now, last time I told you about mole. I gave you 4 formulas to convert given mass into moles, to convert given number of particles into moles, to convert given volume of a gas into moles. And we use probably all of them in today's assignment as well. One of the formula used was volume of a gas at STP in liters divided by 22.4. From where does that relation comes? So for that, write down the next, a very small topic, molar volume. Heading is molar volume. Write down 1 mole of any gas occupies 22.4 liters of volume at STP. At STP, what is STP? I'll tell you, which is called molar volume. Why do we call it molar volume? Because this is the volume of 1 mole of the gas, right? It's called molar volume. Now, what is STP? This is standard temperature and pressure. Abbreviation for standard temperature and pressure is STP. There are 2 things in this. One is the standard temperature and the other is standard pressure. Standard temperature is 0 degrees centigrade, or I can say 273 Kelvin. That is standard temperature. Then what is standard pressure? Standard pressure is 1 atm pressure. Atm is the unit of pressure. Full form is atmosphere. So 1 atmospheric pressure is called standard pressure. There are various units of pressure. Pressure is also used on millimeter scale, used on bar scale, used on Pascal and kilopascal scale. There are various units. In the due course of time, as and when required, I'll keep on telling. Now, I'm sharing one numerical based on molar volume. You'll find this in your, what do you call, WhatsApp. Check your WhatsApp message. You'll find one numerical I'm sharing. We'll solve it. Actually, at the same time, I try to upload these numericals in the chat box of video also. In the chat box also, you'll find these numericals. Okay. The numerical is, this you'll find as Intext Numerical number 7 in the chat box. Calculate number of molecules in 11.2 liters of N2 gas at STP. See, we have to find number of molecules. So relation will be number of molecules divided by Avogadro's number. This relation is number of moles. In 11.2 liters of nitrogen at STP. Now, volume in liters at STP divided by 22.4. This is.
So we don't have to find the number of moles. We have to find the number of molecules.
Yes, number of molecules.
Okay.
Right? We'll find number of molecules only. So second relation for number of moles is this. So number of molecules we have to find out. Is equal to volume in liters is 11.2 divided by 22.4 multiplied by value of Avogadro's number 6.022 into 10^23. This will be the answer. As I told you, as you solve more and more numericals, you'll be able to solve in a much easier method. See, I'll tell you, you can solve by unitary method also. See, 22.4 liters is 1 mole, and 1 mole contains Avogadro number of particles, Avogadro number of molecules. So I can directly say that 22.4 liters contain Avogadro number of molecules. 11.2 contains how many molecules? It comes out to the same thing. Avogadro's number divided by 22.4 multiplied by 11.2, right? So it's just the beginning. In the due course of time, as you solve more and more and more numericals, you yourself be able to apply easier methods. One more numerical. Yes. Calculate the volume of 3.011 into 10 to the power 24 molecules of oxygen at STP. Now, it's up to you the method you want to use. You can equate two of those formulas, or you can use unit method. If you want to use unit method, let me try that if you are able to understand. So many molecules, and we have to calculate volume. We know Avogadro number of particles will be 1 mole. And 1 mole will occupy 22.4 liters of volume, right? I'll go slowly so that you can understand. Avogadro number of molecules will be 1 mole, and 1 mole of any gas at STP will be 22.4 liters of volume. So I can say 6.022 into 10 to the power 23 molecules will be 22.4 liters at STP, and we are given 3.011 into 10 to the power 24 will be how much? That will be the answer. Let me tell you, answer will be 112 liters. Now, if you feel that you are not comfortable with this method, you want to use two relations of number of moles, then number of particles we are given. So I'm writing number divided by Avogadro's number. We have to calculate volume. What was the relation for volume? Volume at STP this volume is in liters divided by 22.4. We have to calculate volume, right? So volume will be equal to number of particles. This is number of particles. Divided by Avogadro's number. Multiplied, cross multiplied 22.4. It will be the same. 22.4 divided by Avogadro's number multiplied by this will be in the numerator. It's up to you the way you want to use. Right? So that was about molar volume, and we tried two numericals as well. Next topic. Molecular formula and empirical formula. I hope you know about a simple compound, hydrogen peroxide. Hydrogen peroxide is H2O2. It is H2O2. I hope you know about the compound ethane. 10th way you might have come across ethane, C2H6. In these molecules, if I divide by the highest common factor, HCF, of number of atoms, 2 and 2, highest common factor is 2, I divide by 2, formula becomes HO. In this case, highest common factor is 2. If I divide by 2, it becomes CH3. So these are molecular formulas and these are empirical formulas. So what is the difference? In molecular formula, we represent actual number of atoms of each element present in one molecule, actual number. Whereas in empirical formula, we represent the simplest whole number ratio of different atoms present in one molecule of the compound. So I'm dictating you the definition. Radon. MF, molecular formula of a compound, molecular formula of a compound represents the actual number of atoms, represents the actual number of atoms of different elements present in one molecule of the compound, right? Actual number, one molecule of the compound. Second definition, empirical formula, EF, of a compound, empirical formula of a compound represents the simplest whole number ratio, between atoms of different elements present in one molecule of the compound, present in one molecule of the compound. For example, I'm giving example in the tabular form in which you'll come to know empirical as well as molecular formula. Compound, molecular formula, empirical formula. Let us say benzene. Benzene is C6H6. Highest common factor is 6. So empirical formula is CH. Ethane. Molecular formula C2H6. Highest common factor is 2. Empirical formula becomes CH3. Glucose. Glucose is C6H12O6. Highest common factor is 6. Divide by 6, it becomes CH2O. That is the empirical formula. Last example, water, H2O. Highest common factor is 1. It means empirical and molecular formula of water will be same. Now, we have studied about percentage composition. We have studied about empirical and molecular formula. Only definitions were required for the next topic. So if we know atomic weight, if we know percentage composition, if we have an idea about mole concept, then all that can be used to calculate empirical and molecular formula of the compound. So right on, the next topic is calculation of EF, empirical formula, and MF, molecular formula, from the percentage composition. Calculate in empirical formula and molecular formula from the percentage composition. Now, this is the topic which can only be explained on the basis of a numerical. So I'm sharing one numerical, not only one, we'll take up one more numerical after that. And this numerical itself will introduce the topic. Check your WhatsApp. So the numerical says, calculate empirical and molecular formula of the compound which contains carbon 36%, hydrogen 4%, and nitrogen 28%. vapor density of the compound is 100. In fact, this numerical should be solved in a tabular form. Keep on drawing the table with me. Elements. We'll write symbols. It contains carbon, hydrogen, and nitrogen. Atomic weights. Atomic weights of these elements are carbon 12, hydrogen 1, nitrogen is 14. Percentage of these elements we are given. Percentage of carbon is 36%, hydrogen 4%, and nitrogen is 28%. Now listen carefully. Before we proceed further into the numerical, the very first thing you should do is add these percentages. Some of these percentages should be 100. But in this case, when you add, this comes out to only 68. If it is not 100, then it is understood. I'm repeating, it is understood that leftover is oxygen. So next element is oxygen. Atomic weight is 16, and this is leftover, that is 32. But at the same time, be very careful. In case you are given that a hydrocarbon contains 20% hydrogen, rest nothing is given, then you know hydrocarbon contains carbon and hydrogen only, does not contain oxygen. So don't think that it contains 20% hydrogen and 80% oxygen. See, this is hydrocarbon, does not contain any oxygen. So understood that leftover 80% will be carbon. Right? Now, next, this table we can close here. Next step will be atomic ratio. Now, in this column, calculations will start. Atomic ratio is percentage divided by atomic weight. We divide all these percentages by atomic weights. 36 by 12, 4 by 1, 28 by 14, 32 divided by 16. For this numerical, I will use a very simple data because I just want to make you understand how to solve. Next column will be simplest ratio. Simplest ratio. Simplest ratio is atomic ratio divided by smallest atomic ratio. I'll read it out for you. Simplest ratio is atomic ratio divided by smallest atomic ratio. So we divide all of them by the smallest number, that is 2. So this will be 3 by 2, 4 by 2, 2 by 2, 2 by 2. Next column. Whole number ratio. This is the last column, right? Whole number ratio. This last column is used only if one or more of these numbers is a fraction. If all of them are whole numbers, then last column is not required. We have one value as a fraction, that is 1.5. Now we'll multiply all these numbers by a smallest whole number so that they are all converted into nearest whole numbers. If you could understand, tell me, I should multiply by which number?
2.
2. So multiply by 2, it becomes 3, 4, 2, and 2. Now, further, I'll be writing below the table. Therefore, I'm rubbing this table. So next, we are getting first answer. Empirical formula will be carbon 3, hydrogen 4, nitrogen 2, oxygen 2. This is one answer, empirical formula. Now we have to calculate molecular formula as well. Now, how to calculate molecular formula? Molecular formula will be empirical formula multiplied by N. Multiplied by N. Now, what is this N? N is molecular weight divided by empirical formula weight. Empirical formula weight. Like we calculate molecular weight by using molecular formula, similarly, we calculate empirical formula weight by using empirical formula. So, empirical formula weight will be C3 36 H4 4, N2 will be 14 into 2 28, O2 16 into 2 32. This is 100. So I know the value of denominator. Now I want the value of numerator, that is molecular weight. Now look at the numerical. We are given vapor density of the compound is 100. I taught you about vapor density in the previous class. Molecular weight will be 2 into vapor density. So this will be 2 into 100, 200. It means value of N will be 200 divided by 100. Value of N is 2. This is 2. So molecular formula will be whatever was the empirical formula, that is C3H4 N2O2 multiplied by N, that is 2. This will be C6H8 N4O4. This is molecular formula of the compound. On the similar pattern, with of course slight change, we'll solve rather not only one, two more numericals, because there'll be different type of data which can be given in the numerical in the exam. So this is the next numerical on a WhatsApp. Now the numerical is a compound contains carbon this much, hydrogen this much. If you add these two, it is not 100. It means leftover will be oxygen. 0.1 mole of it weighs 6 grams. 0.1 mole weighs 6 grams. From this, we'll calculate molecular weight, which will be used to calculate the value of N. Calculate molecular formula of the compound. So in short, I can say it contains carbon, hydrogen. Carbon is 40%. Hydrogen is 6.67%. It means leftover is oxygen. This will be 46, 47, 53.33. Atomic weight 12, 1, 16 is, I'm solving in short. Atomic ratio will be this divided by 12. I'll tell you, this will come out to, no, I don't have the value. This will come out to 3.33. This divided by 1, 6.67. This divided by 16 will be 3.33. Next was simplest ratio. Divide all of them by the smallest value. I'm directly writing. This divided by same number 1. This divided by 3.33, 2. This divided by 3.33, 1. Last column is not required because all values are whole numbers. It means empirical formula will be CH2O1. CH2O1 is the empirical formula of the compound. Now, for molecular formula, we need molecular weight. See, what is molecular weight? Molecular weight is nothing but weight of 1 mole of the substance. Simple words. Weight of 1 mole of the substance is molecular weight. We are given that 0.1 mole weighs 6 grams. It means 1 mole will weigh 60 grams. So molecular weight is 60. So 0.1 mole is equal to 6 grams. 1 mole will be 60 grams. That will be the molecular weight. Now here itself we can calculate empirical formula weight. Empirical formula weight will be carbon H2, 1 oxygen atom 16. This is 30. Molecular weight is 60. It means value of N is 2. Molecular formula will be empirical formula into 2. That is double of this will be the answer. So molecular formula will be C2H4O2.
So how did we calculate the empirical formula weight? And could you explain it again, please?
1 carbon 12, 2 hydrogen atoms 2 into 1, that is 2. 1 oxygen atom 16 into 1. As we calculate molecular weight by using molecular formula, similarly we calculate empirical formula weight by using empirical formula. Exactly the same, right? Now one more numerical. In this I'll tell you how to save time, because in 11th and 12th standard time will be a very important factor. You should not miss any numerical, any question due to shortage of time. So check your WhatsApp message. We are given 20 grams of a hydrated salt. What is a hydrated salt? Hydrated salt is that which contains water of crystallization. You know, copper sulfate pentahydrate, CuSO4.5 water. That .5 water is 5 molecules of water crystallization. That is why we call it copper sulfate pentahydrate or hydrated copper sulfate. If there's no water of crystallization, then we call it anhydrous copper sulfate. So 20 grams of a hydrated salt contains iron this much, sulfur this much, and oxygen so much, and rest water. If it says rest water, it means will not take leftover as oxygen. It is mentioned in the numerical to rest water, water crystallization. Calculate molecular formula. Vapor density is 139 and atomic masses of iron and sulfur are given. See, we are not given percentage of elements. It means we'll have to first calculate percentage of each element in the compound. I'm just explaining this, how to calculate percentage of different elements in the given compound, but we can avoid that. That's what I'm going to tell you in this numerical, how to save time, how to avoid extra calculations. First of all, if I want to calculate percentage of iron, it's given 20 grams of compound contains 4.028% iron. So percentage of iron will be 4.028 grams iron divided by total into 100. This is percentage of iron. Similarly, we can calculate percentage of sulfur, percentage of oxygen, and leftover will be water. We need not calculate percentage of hydrogen and oxygen in water, use water as such. But there's no point calculating these percentages. Save time. No point calculating these percentages. Now, what do we do? In calculation, one of the column was I wrote percentage of each element in one of the columns. In place of percentage, use masses of different elements. Use masses of different elements and then proceed in the normal way, normal manner. So I'll solve that way. Elements are iron, sulfur, oxygen, and in place of one of the elements, I'm using water because rest water, remaining is water. Although water is not an element, I've written that water in this column. Iron is 4.028. Sulfur is 2.306. Oxygen is 4.602. Total compound is 20 grams. 20 minus these three will be water. And I'll tell you, this water will be 9.064. Now, atomic weights. Iron 56, sulfur 32, oxygen 16. For water, actually water is a compound, so we'll be using molecular weight in place of atomic weight. It will be 18. Next will be atomic ratio. I'm writing directly. This divided by 56, atomic ratio will be 0.072. This divided by 32, atomic ratio will be 0.072. This divided by 16, I hope you're writing. I hope you're writing. Atomic ratio will be 0.288. And this for water divided by 16, this atomic ratio will be 0.503. Right? Next column is simplest ratio. We divide all of them by the smallest number. And the smallest number is this. Divide by same, divide by same, divide by 0.072. It will come out to 4. This divided by 0.072, this will come out to 7. It means empirical formula of the compound will be iron 1, sulfur 1, oxygen 4, and this is water of crystallization. We'll write it as 0.7 water. This is the empirical formula. Right? Now we proceed further. Little more is left. We have to calculate molecular formula. We are given vapor density. Vapor density is 139, means molecular weight will be double of that. Molecular weight will be 139 into 2, 278. Now, for this empirical formula weight, will also be 278. It means value of n is 1. And if n is 1, it means molecular formula and empirical formula, they are same. So value of n, 278 by 278. So molecular formula will remain the same. FeSO4.7 water. Right? So with that, we finish today's class. Anything you want to ask? Maybe I was fast today because topic was easy. Topic was pretty easy. Anything you want to ask, Dylan?
Yeah, sir. In one of the in-text questions, we had to calculate the number of molecules in 11.2 liters of nitrogen at STP.
Yes.
So basically, after a calculation, we had to multiply